Let's go back and review a little bit. We're in 15.5, or going back to 15.5 to review some. And we'll go on to cylindrical coordinates and spherical coordinate systems. So we'll get caught up as we go here. So when you look at a triple integral, if the integrand is 1, right, then you're looking at those little tiny cubes in there. Well, they don't have to be cubes, they're rectangular solids, right? And then you add those all up. So your delta V are these little cubes you add up. And you can interpret it as a region underneath the surface. And in this general case, it's in the XY plane, but it could be in a different plane and going to a different direction like that. So you do your norm of the partition, it goes to 0, etc., and you get your triple integral. So we looked at this example. Hopefully you worked it out, got your answer. This is a rectangular solid. So this is, you're not going to really see this, in like an exam or anything, but it's a good start to get used to integrating individually. So it's kind of like partials. You got to integrate and hold the other variables constant. Okay, so then we went to this question as setup. So you do your f of x, y function in 3D. And so you would graph that, and so it's the area underneath it. So you want to look at your region here, right? I guess I have it there in the XY plane, and that's what you do that first. So it's like a double integral and then times the height. Well, the height is going to be the difference here, right? So that's your function. So there's your lower limit to your upper limit. So your z equals 0 to z equals the function. Oh, and also I'm going to try to do this in portrait form instead of horizontal. See if I can get more on a page to discuss things. See how it goes with the videos. I'll check it out. And here's our next example. Find the volume. This was when it starts to get a little different, right? So you have your cylinder. So it's that parabola. And then your z value is arbitrary. And then when you project that down, it's integrated over this region. So your lower limit to upper limit. And then the height is z equals 0 to the plane. So this was the plane here. Okay, then we worked it out, or hopefully you worked it out and got your solution. Okay, so those are somewhat reasonable. When we get to applications, 15.6, we want to just focus on 29 through 34 only. So what that is then essentially is, so this is looking at mass. So this is center of mass, moments of inertia, and all that kind of stuff. We're only going to look at calculating mass. So mass is volume times density. So if the volume, of course, changes, then you're going to have a different mass as you add stuff up. So now this is the case where the density is varying. And so density is different for each point. Okay, so that's that's what we want to focus on. So we did this question for setup. A solid Q is bounded by the cone and the plane, and then it tells you a function for density. The density is directly proportional, didn't mean to do that, is directly proportional to the square of the distance to the origin. So the distance is like the distance formula, right? It's the square root of some of the squares, but it's the square of that, right? That's the cone. So the distance formula is the square root of the sum of the squares. But it's directly proportional, which is your k, and then you square it. So that's where the root's gone. And so they're using that function notation, the delta of xyz. So that gives you, so it's not really like a fourth dimensional graph. It's really a density function at a point. So that's what makes it a little different. And then you integrate around the region. So here's your R, your region in the xy plane. You integrate around that, lower limit to upper limit, right? And then you go left to right. Again, your outside, on the very outside should be your constant limits of integration. Okay, so we didn't actually evaluate this. It actually is really messy to evaluate. So next we get into 15.7. This is triple integrals in cylindrical and spherical coordinate systems. So draw in a coordinate, so basically cylindrical. So draw in a coordinate system like this. So here's your coordinate system like this and this, right? And what it is basically polar in the xy plane, or the polar region, right? So this is your xy. Or you could consider, of course, this is the positive direction is your polar axis. And so you have everything to do with polar in polar coordinate systems. But then you just basically multiply by the height. So the height is your z. So there's your z, and that's your function of r theta. So you have f of r theta z as your integrand. So then, just like polar, you end up with your extra integration factor. Oops, I keep doing that. Your extra integration factor r for your function. So cylindrical is really polar, and then adding in the z function. And so you need to have z as a function of r theta. That's what's key. So if we go back to, and this is getting into the new stuff here, I'm pretty sure. If you go back into this example, this is the same one we did above. So if we have, so same question, solid bounded by the cone and the plane, so it's cut off at z equals 2, integrate around the circle. So you want to basically change this to polar, and then it times the height, which would be your z function. So when you have your z as a function of xy, right? So that's like your f of xy. So this is your f of xy. Then you can essentially substitute directly for your xy squared for your limits of integration. So we're going to say z equals the lower limit to z equals the upper limit, and then integrate around, in this case, the circle using polar. So, and then the density was described the same, directly proportional to the square of the distance. So that has to be distance formula. You might get other ones like directly proportional to the distance from the z-axis, or like the xy plane, and then this would just be z instead of the distance. So the distance, right, is it's a point. You have 2 points in space, and you calculate the distance formula. But the distance from the xy plane would just be z. Okay, so think about that. So that's another case you'll see. So then when you set this up, you're converting your density function into r plus z squared. So that's a direct substitution for your r squared. Z remains z. Then you go z equals the cone to z equals 2. So the cone is that, so that's just your r, because, right, x squared plus y squared is z squared, which I didn't really show that, but you're doing this substitution right here, right? So that is your r squared. Let's just change that to here. So that's like your r squared. And you take the square root and you get r. And yes, technically that would be absolute values, but we're talking about a distance from, it's a positive value. So we know that. So then when you set it up, this is a much nicer function to integrate. Your mass is r to 2, 0 to 2, 0 to 2 pi. So this is around the circle. And then your substitution. This becomes just a polynomial, basically. All right, so check that out, evaluate it, see if you can get your function there. Okay, so this is going on to the next question. I blocked out a couple pieces there before we move on as we get going here. So, where's our next question? All right, so evaluate and convert from rectangular to cylindrical form. So it looks really messy here, and here's the key. You can substitute directly for x squared, y squared. That's okay. But your limits of integration, you have to do separately. You need to draw that graph, whatever that's saying, and then change that to a cylindrical form. So what we need to do is realize what is z equals x squared plus y squared, and z equals 2 minus x squared minus y squared. So take a moment to think about that. What's that graph? Okay, and then I'll do it here. Okay, so that's basically a paraboloid that opens up and a paraboloid that shifted up 2 units and opens down. So that's what I have in there. So you can see then I have z equals r squared, which is the bottom one, to z equals 2 minus r squared. So it's substituting x squared plus y squared for r squared. Okay, so it's here to here. Okay, and then what you're doing then is you are integrating around the circle in the xy plane. So that's over here. Erase some of this stuff. I think it's here. Okay, so there's your circle in the xy plane. And you would look at this function, right? That's basically y, right? Y equals negative y root 1 minus x squared to y equals root 1 minus x squared. So you got to draw that. It's the lower half to the upper half. Lower half to the upper half is what you're basically doing. And then negative 1 to 1, right? So x goes negative 1 to 1, here to here. So then you change that to polar. Okay, so that's all the rest of this. Okay, so there's my y equals changing to polar, so you get this form here, which is that circle. So then you integrate around in polar. Oops, wrong. I was going to erase that. Okay, so there's our polar form. And I should have gave you time on that. Sorry. So you go from your lower, which is substituting this for r squared, and then 2 minus r squared. So you get z equals this to z equals this. Substitute directly for x squared plus y squared, which is this. And then this is around the circle, right? You got r0 to r1, and then 0 to 2 pi, all the way around. And then we have our r dz dr d theta, and going all the way around that circle. Okay, and I don't have the solution to that, so work that out. Shouldn't be too bad, right? Because now you have just a polynomial again. This will just be r, I mean, we'll show you a couple steps here, right? That's just r cubed and then r. So you're really just doing r to the fourth. So dz is just z, and then you're going to evaluate that from r squared to 2 minus r squared. So you end up, again, substituting these in, and you just get a polynomial. Okay, so check that out. I'm going to go ahead and erase this. I don't want it cluttering there, my notes. And there will be a number of just setup questions on the final, so you'll be able to do that. Okay, let's then maybe have another example. I don't have one handy, but I'll just put a placeholder here for later in case we want to do something. Maybe next time I'll do that first with a video, at least set one up for you to look at. Let's go ahead and pause it there, and we will just go ahead and do another video as we just do this, as we ramp up our lectures on this. I'll go ahead and pause that now.